Okay. So my wife is exactly 6 months younger than I am to the day. I'm July 26th, 1983. She's January 26th, 1984. Yeah. Is that? It's a good date. That's good. How old's your brother? Nice. Well, I like my birthday. I think it's well positioned. I think it's a good number. I like 26 as a number. It's good. It's like got factors. Divisible by 13. I think that's interesting. Like 2. Anyway. Okay. So let's start with some statements about Britt. So you know my age. I'll tell you why I don't use my age in a minute, just because it rounds, her answers round so much more nicely. So my wife is 39 years old. And she's from January 26th, 1984. So we can confirm that that's true because she'll be 40 years after this, which would be January of 2024, right? Which hasn't happened yet, right? Is that cool? We can all agree on that. So that's a true statement. So that one I'm going to pre-put as true. All right? Cool with that? I'm going to put a few other statements up here, and I want you to tell me if they're true or false. Does that make sense? Okay. So we have one obviously true statement, and then we'll talk about the others. True or false? This one, true or false? Yeah, that's right. Next month will be December. She'll be 39 years and 11 months old. Month after that will be January, and then in that month she will turn 40 years old. 12 months later. Makes sense. Good. Okay, true statement. She's 40. True or false? Well, that's obviously true. In fact, I'm going to go ahead and say this is false. We'll get back to that. Why, as a science guy, am I going to say that this is false and that's true if this is true? And this is true. Yeah, the truth is that the way we round birthdays is the only thing we round that way, right? Anything else, once you get halfway, you round up, right? But age, we have this thing where we're like, no, I'm 40 and I'm going to be 40 until like 2 minutes before my birthday. Then I'm 41, right? We don't round anything else that way, right? But so from a scientific perspective, nah, sorry, Britt, you're already 40. Because once you pass that 6-month point, the truth is my birthday is the day we should start calling her 40, the next number every year, because I'm the halfway point for her, right? I'm directly halfway through the year for her. I think she probably wouldn't have appreciated. She threw a surprise birthday party for me this year for my 40th, which is very nice. There are like a lot of people there. I don't really like things like that, but it was actually nice. But she probably would have objected to me like starting calling her 40 there. But yeah, this is true specifically to the nearest month, right? I guess I should go green since we said it's true. Yeah, to the nearest month, this is true. Right? This is true to the nearest year. This one. Is there any way that we can think of that's true? To the nearest 10 years, she'd still be 40. I mean, I guess you could say, if you're counting by 50s, right? That's not something we do very often, right? But if you're counting by 50s, would that be true? Yeah. Is there any way you could say she's 100? No, because even if you count by the nearest 100, well, if you count to the nearest 100, she'd be 0, wouldn't she? Does that make sense? Now, this may seem kind of pedantic, but I want to show just something as simple as how old somebody is. We can actually make a bunch of different statements that are all true. Does that make sense? Numbers are interesting that way. Anything that's measured has been rounded to some extent or another. And if any number is rounded, how it's been rounded matters. Does that make sense? You can say a lot of things that are true if you round in key ways. All right, I got a handout for you here, and we're going to talk about that. So today we're going to talk about something I've been kind of teasing at, which is like we're going to talk about rounding and how many numbers to use and things like that. Here we are, we're finally at the day. So there you go. Welcome. So, I hate sitting here to do this, but that's okay. So, before we get talking about what to do with it, let's just talk about the fact that everything we measure is rounded. There's no way to know the exact mass of something. Because whenever we measure the mass of something, we are comparing it to something. It used to be that we actually had scales, balances, right? Where you'd put a weight on one side and the thing on the other, and you'd wait till they balanced out, right? Now we use digital scales, which have a piece of metal that bends, and they measure how that adjusts the voltage. But like the voltage that's being measured is just to a certain precision. Does that make sense? And after that, it's anybody's guess. Everything's measured to the nearest something. You measure something with a ruler. If that ruler only has millimeters on it, then you can only measure it to the nearest millimeter, right? I have calipers at home, a very, very, very precise. It'll measure to the nearest thousandth of an inch. It's really precise, but it's still not infinitely precise, right? There's still a limit to it. Does that make sense? So let's look really here. This, what has this been measured to the nearest? Yeah, to the nearest 1 milliliter. What about this one? Nearest what? Yeah, that's right. It's measured to the nearest decimal 1 or to the nearest tenth of a milliliter. I'm fine if you say 1 decimal place of a milliliter. That's cool. This is obviously measured to the nearest 1. And what unit's that? Yeah, 1 meter. Good. And then this one. And this one maybe has you scratching your head. As me scratching my head. What could this be? Yeah. This could be to the nearest 100 grams. This could mean 85 would be cool. 110 would be cool. Does that make sense? Or it could mean that it's to the nearest what? It could mean that it's to the nearest 1 gram. 100 exactly, not 99 and not 101. It could also, I guess, be to the nearest 10 grams. Does that make sense? We don't know. In fact, what we know is this. If you measure this and it says 23 mils, what that really means is that it's got to be what would round up to 23? Well, like 22.6 would round up to 3, right? And what would round down to 23? Sure, even bigger, 22.3 would round down, 22.4 would round down, and 22.5 would round down. In science, whenever we get a 0.5 exactly, we go to the nearest even number. That's a science rule. So 22.5 would round to 22, 23.5 would round to 24. Sorry, I should have put a 3 here. And yeah, that would round to 24. So sorry, 23.4 would be the nearest one to round down. Does that make sense? So does that make sense? This is the range that represents. Anything in that range measured to the nearest milliliter would come out as 23. Does that kind of make sense? And we're not going to write this every time, but I want to start thinking that. If we had 13.4, what's the lowest possible number that would round to 13.4? Well, 13.3, and I need a number that would make this round up. So 9 would make it round up, 8 would make it round up, 7 would make it round up, 6 would make it round up, and 5 would make it round up. So 13.35 is the lowest number that could have given us this. What's the highest number that could have given us this? Yep. Nope, because that would give us this. But what about 13.41? Would that give us this? Yeah, so 13.41 would give us this, 2 would give us this, 3, 4, and 5 would give us this. Does that make sense? Because again, those 5s always round to the nearest even number, and that 4 is even. Does that kind of make sense? If the real thing weighed anywhere in this range, that's what it would give us, or not weighed, sorry, this is volume. If the real volume was anywhere in that range, if we put it in something that only gives us the nearest milliliter, that's the number we're going to get. Does that kind of make sense? How's that feel? What about 123 meters? What is the smallest number that could possibly, the thing is really this long, it would round to 123 meters? Well, 122, and then what's the smallest number that would round up to 123? Yeah, 0.6. And going above 123, what's the biggest number that would round down to 123? 0.4. Good. Does that kind of make sense? Be honest. Does that feel kind of okay? Now this 100 gets messy, because if we take it to be to the nearest gram, then that would mean that anything 99.5 to 100.5 would round to 100. Does that make sense? But if we take it to be to the nearest 100 grams, in other words, we're measuring to this number, well then anything above 50 would go up, right? 51, I guess. And anything below 150 would round down. Does that make sense? That would be to the nearest 100. This would be to the nearest 1. What about to the nearest 10? What would the range be then? If we're rounding to the nearest 10, what number would get us to 100? Well, 90 would round down to 90, 91 would round down to 90, 92 would round to 90, 93 would round to 90, 94 would round to 90, but 95, well, that would round up to 100. Does that make sense? And 101 would round down, 102 would round down, 103 would round down, 104 would round down, 105 would round down. So that's to the nearest 10. And what I want to stress with you is these zeros make it that any of these could be true. Does that kind of make sense? The number doesn't tell us if it's got these weird hanging zeros in it. Does that kind of make sense? So when we round numbers in science, or even before we round them, we want to be able to look at any number and say, hey, the person who took this measurement, where did they round? How significant is this number? Or in another way of saying, how precise is this number? How closely was it measured? Does that make sense? Was it measured to the nearest 1, to the nearest 10, to the nearest 1,000? Because here's what you don't want to do. You don't want to take one measurement that was incredibly accurate, and mix it with another thing that was measured really kind of lazily and just not carefully at all, put them together, and then treat the new measurement like it's really accurate. Does that make sense? For example, if you weighed one of my hairs and found that it weighed like 0.001 grams, right? And then you put me on a scale and you found that I weighed, 108 kilograms, so that'd be 108,000 grams. Does that make sense? If you then go and hand me, while I'm standing on the scale, that extra hair that you've already weighed, do I now weigh this? Does that make sense? No, because it's not like I weighed 108 kilograms measured all the way down to the third decimal place of a gram when I was on the scale, right? It stopped measuring here. Does that make sense? So all of this is a mystery. So I can't change these last numbers. Does that make sense? And that intuitively makes sense to us. If you stood on a scale and somebody came and handed you a speck of dust, you would not expect your number on the scale to change. Does that make sense? Because we're measuring at different levels of significance. We're measuring to a different number. Does that kind of feel okay? That's what today's about. So we're going to look at numbers today, and what we're going to say is when we look at a number, we want to know how many of those numbers are meaningful, how many of them are significant, so that we can know how to do math with them. All right? And at first, this is going to feel a little weird or clumsy, and then when you get going, you'll get good at this, I promise. Today, we'll kind of write this down, and you'll go a little bit like, wait, what? Why do I care? What's this? And then in the coming days, we will do math, and every time we do math, we'll say, okay, now let's look at our digits. How many do we want to round to at the end? And you'll get a feel for it. Do you trust me? Ha! You shouldn't. Anyway, let's get to it. So what we want to look at is, of these numbers, this number here, 132 grams, how many digits in this number? 3. Okay. I'm going to tell you that all 3 of those are significant. And we call these significant digits or significant figures. And usually we use the short form sig figs because we're lazy. All right. Now, how many digits are in this number? 3. Yeah, but I'm going to tell you only one of those is significant. And I want you, while I tell you this, see if you can figure out the rules of what we think matters and what we think doesn't. This number here, I'm going to tell you how many digits are in it. And I'm going to tell you that all 4 of them are significant. How many digits in this number? 1, 2, 3, 4 again. I'm going to tell you that only one of these matters. You getting the rules yet? How many digits here? 1, 2, 3, 4. And I'm going to tell you that all 4 of those are significant. And over here, how many digits? 1, 2, 3, 4, 5, 6, 7. Anyone want to take a guess at how many of those I think are significant? Nope. All of them? Nope. 3. All right. What about this number? How many digits? 6. How many of those do you think are significant?
I think it looks like all of them.
Yeah, good. So we'll talk about why. So what the hell's going on here? I'll give you a couple easy ones, which is that like 215, 197.24. This is 3. That is 1, 2, 3, 4, 5. First of all, what's the only digit that sometimes counts and sometimes doesn't? See if you can figure the rule there. The only time we even have to worry about it is if this digit is present. Yeah, cool. So that's the first rule. We're going to write some rules. Let's write them here. Our first rule is this. Any non-zero digit is significant, had to be measured. Because what we're really trying to get out of here, the real question is, hey, if there's zeros, do those zeros mean they were carefully measured, or are they just blank? What do we call a zero that's only in a number to show you how big the number is? You use this term a lot in elementary school. They'd say that zero is a... maybe, but the word I'm looking for, do you ever use the word placeholder? Did I ever tell you that? Zero is a placeholder. It gives you the place value. Did you ever talk about the place value of number in elementary school? Maybe that's not something they teach so much anymore. When I was a kid, we spent a lot of time talking about the place value and the placeholders. But 0 is the only placeholder. Does that make sense? In other words, if you wanted to say how much money was in, let's say, you guys might not know this. Did you guys know that Victoria, very, very, very rich? You may not know this. Victoria's real name is actually Jeff Bezos. She owns some big company. I can't remember what it's called. But if she was going to say how much money she had, what would she probably say? Let's say she's worth $68,341,275,000.41. That's what's in her bank. I mean, nobody keeps that in their bank. Rich people have investments, but let's say they did. Is she going to tell you that number specifically if you ask how much money she has? No, the news would probably say she's worth $68 billion, right? Which looks like this. Now, all of these zeros we know are really just rounded. But why do we have to still write them? Well, because if we just wrote this, then it looks like how much money she has. It would look like she just has $68. That's more what my bank account looks like, right? So these zeros are what we call placeholders. Their job is they don't give us meaningful information, right? In other words, it doesn't mean that she has $0, $100,000, or $0 million, $100 million, or $0, $10 million, or $0 million, or $0, $100,000, or $0, or so on and so forth. Does that make sense? I missed a whole set of zeros there when I rewrote it. All those zeros are just telling us, like, this belongs in the billions column. Does that make sense? Those are the millions. Those are the thousands. That's all they do. They don't give us meaningful information other than place value. Does that make sense? But then some zeros very much matter. For example, my grandmother lived to be 109. That zero isn't just a placeholder. It doesn't just tell us, oh, she lived around about 100. It's saying she lived 100 years, but then she didn't live any decades beyond that. She didn't make it to 110. How many years beyond 100 did she make it? 9. So this number matters. Does that make sense? It's not just a placeholder. It's specific. It's telling us that she lived 100 and didn't make it to 10 past 100, but we did make it to 9 past. Does that make sense? I could have said about my grandma just as easily, I could have rounded and said she was 110 years. And that would be true, right? It's rounding, but it's true. I could have just said she lived to 100, right? That's also rounding, but it's true. In each case, this is different. If I say, my grandma lived to 100, these are just placeholders, right? I'm just speaking roughly. Does that make sense? If I said she lived to 110, this is a placeholder. It's just saying, we're not saying she made it to 110 exactly. We're saying she made it to 110, and that's just showing you that she didn't make it to 11. It should be a very different story, right? Somebody dies at 11, that's very tragic. Somebody dies at 110, you go, that's a pretty good run. Not by my standards. I, of course, am going to live for hundreds of thousands of years as a brain in a jar with robot spider legs. But for most people, 110, good long run. Does that kind of make sense? So some zeros matter. Some zeros are precise. They mean 0. Not 1, not 2, not 3, not 4, 0. And some zeros mean this is just an empty space where a number fits, but we don't know what that number is. Does that make sense? Sometimes a 0 means we've already rounded, so we don't know what number goes here. So I'm just putting a 0 there to show it's been rounded. And other zeros mean this is exactly 0. And we try to tell the difference. Does that make sense? So, rule 2, some zeros count. So some zeros are significant. And some are not significant. Does that make sense? And what we're going to try to get is when do zeros count and when don't they? Does that make sense? When do zeros count? When do zeros not count? And again, if this all seems silly, you just have to trust me that makes a big difference in science, because if you use really rounded numbers to do really important work, bridges collapse and people die, or spaceships skip out of orbit and float off into space and billion-dollar projects never land. And these things happen, by the way. The Chinese and the Israelis a couple of years ago both had lunar landers crash on the surface of the moon and not make it there. And the math wasn't precise enough. They didn't account for enough things. It does matter. So here, we said 100, we said only one of those numbers can we assume to count. Unless somebody told us specifically this means 100 exactly, we assume that zeros at the end of a number and notably, what doesn't this number have in it that this one does? Because here we said all these zeros matter. What does this number have that this one doesn't? Yeah, so zeros at the end of a number without a decimal place, we assume don't count. Oh, shoot, this is supposed to be in the not significant column. And here I'm writing it in the significant column. I'm sorry. So this one here tells us that zeros at the end of a number that's not. I'm sorry, I will erase that highlighter. And I'll just put a little dot next to it so you can see which one it came from. Zeros at the end of a number without a decimal place. They don't count. On the other hand, here we see that zeros at the end of a number do count if we've put a decimal place there. And do you know why that is? Because if somebody meant 100, just about 100, would they write this? If somebody writes that, does that say to you, about 100? No, in fact, if you read this out loud, you have to say 100.0. Just the way it reads tells you somebody bothered to put the decimal place in the zero. Does that make sense? So we assume if somebody bothered to write all that they mean that's exactly zero. Not a placeholder, that's exactly zero. That's not a placeholder, that one's exactly zero. That, not a placeholder, it's exactly zero. Because why bother writing the decimal place in the zero if you didn't mean do this exactly? Does that make sense? So any zeros after a decimal, like any zeros at the end of a number after a decimal place, we assume, well, that was a waste of time to write unless they meant it. If you saw a price on the menu that said 3.00, and then when you got to the cash register, it was 338, 328, and they're like, oh no, we had rounded it. You'd be like, no, you didn't, because you went to all the trouble of writing decimal 00. So give me my 28 cents back. And they'd probably fight the cashier at Target. You'd be like, all right, Target lady, you and I are fighting now. Does that make sense? If somebody is bothered to write zeros at the end of a decimal place, we think they matter. All right. Now here, we said these zeros obviously don't matter. And then here, if we follow the rule we just did, those zeros at the end of a number after a decimal place do matter, right? Do we see that? Because that's what the rule here says. Somebody bothered to write these, which brings this up to 1, 2, 3 sig figs. But all of these zeros, we say are just placeholders. Why is that? Well, the answer is that on the scale, if you put something on the scale and these numbers haven't changed yet, it means that the thing wasn't heavy enough to make numbers appear there. Does that make sense? So all these are is placeholders. They're just saying the number didn't get this big. The number didn't get this big. Does that make sense? So any zero before a non-zero number doesn't count. It's just a placeholder. Any zero before the first non-zero number doesn't count. All right? I'm just going to say is a placeholder. You have to write it, because if instead of writing 0.003 grams, you just wrote 3 grams, it would give you the wrong number, right? So you need those zeros. The placeholding function is very important, but they're not giving us any information other than place. And then finally here, we said all of these matter. Well, that's a 0 at the end of a number. And we said they count because of rule 2. But the other ones that count is any 0 that's surrounded by non-zeros always counts. So if it's inside of a number, it counts. So any 0 surrounded by non-zeros always counts. And that's it. And with a bit of practice, you'll get really good at this. And again, we'll talk about it a lot. But you've got your rules there. There's actually a space on the next page to write the rules neatly. Maybe I'll rewrite that at some point, but I kind of like this spot here. I think when I do this, when I redesign this note, I'll write it that way. So instead, in the next page where it says the rules, let's just give a few examples and you just tell me how many sig figs they have. Okay, for each of these, just take a minute and just tell me how many sig figs they have. I'm going to give you, 2.5 minutes. Plenty of time. Write them down. I know it says the rules on that page, but that's fine. Don't write the rules. Write that. Good. All right, let's take a look at these. Shall we? Shall we? You adventurous lot, you excitable crew. Okay, 143. How many of those digits are significant?
3.
Yeah, all of them, right? Because there's no zeros. 211.45.
5.
Yeah, good. 200?
1.
Yeah, could be 1, 2, or 3. And since we don't know, we have to assume 1. Right? Those zeros, we have to assume that they don't count. Now, if somebody said to you 200 exactly, then you can say, okay, that's 3. Then we know. But unless they say that, we have to assume. Does that make sense? 220. What do we have to assume there?
2.
We have to assume 2. Now again, if somebody said 220 exactly, you could say, oh, cool, all 3 of those. But failing that. Here, 107.4.702.
All 7.
All 7. Good. 103.00.
3.
No. 5. Because these ones, why bother writing them? Yeah, these zeros you have to write, right? Because if you don't write these 2 zeros here, 200 would just become 2, which doesn't make any sense, right? But here, 103, if you wanted to write that, you could just write 103. So if you're going to bother to write decimal 00, we're going to assume those 2 zeros matter. They're good. So that would be 5. But here, yeah, beautiful. Those are just placeholders, right? They don't tell us anything except that we haven't got there yet, right? If you think about how numbers get made, as you get bigger, these numbers start going up. So like you can't round and have the numbers in front turn into zeros. When you round, it's the numbers in the back that turn into zeros. Does that make sense? So there's no way that these zeros can tell us anything except where the place value is. Another way to think of it is this. If I walked 25 centimeters, which is about my kind of exercise, well, that would be 0.25 meters. Well, here it was 2 sig figs, right? So it's the same number here. So it's still got to be 2 sig figs. Does that make sense? And then if I converted that to kilometers, that would be going 0.00025 kilometers. Well, it's the same number. So how many of those digits are significant? Still just 2. Does that make sense? All these are placeholders. Does that kind of make sense? Cool. All right, here. Oh, yeah, these 3. Good. Okay, now why do we care about this? We care about this because it tells us how to round. Right? That's why we care. The reason we do any of this crap is that when the time comes, it tells us how to round our final answer. Does that make sense? And when you're multiplying and dividing, here's the rule. You count the sig figs of each number, and then your answer has to be rounded so that it has the same sig figs as the lowest of the numbers you used. Does that make sense? In other words, you know the expression like you're only as strong as your weakest link, right? Right? So if you build a chain to like hold a bike up in the ceiling of your roof, and it's like steel loop, steel loop, steel loop, steel loop, fruit loop, steel loop, steel loop, how strong is your chain? It's as strong as a fruit loop. Does that make sense? It doesn't matter that every other loop is made of steel. That one fruit loop you put in there, is it going to hold that bike up against the ceiling? No. Does that make sense? Same with numbers. When you're doing math, you can only say your final answer is as accurate or as meaningful or as precise as the least precise number you use to make it. Does that make sense? So let's do an example. Everyone, let's do this together. And you'll need a calculator to do the math. 3.502 times 1.84 divided by 2.6 equals what? All right, so do that on your calculator. Meh. Oh, sorry, I thought I'd join it. It sounded like you were having a good time. Wake up! Okay, I've got some battery now. I can walk around finally. I'm feeling hemmed in being here at my desk. Oh, blessed coffee. How do I love thee? Let me count the ways. 1, 2. Coffee, shall I compare thee to a summer's day? Thou art more lovely and more temperate. Would you like coffee?
I love coffee.
Would you like a coffee? You sure? Yeah, offer's on the table. It's right there. I'm not drinking it all. I don't know if I'm... Oh, talk to me. Guys, calculate this. This is not some challenging question. Use a calculator to get the answer. If you have a calculator, go stand up and get one. You got legs, they work, right? Victoria, as I'm aware. They didn't fall off at some point while I wasn't looking.
Mine did.
If they did and I'm being horribly insensitive right now, I do apologize. My uncle has no legs. Oh, I'm sorry.
My legs are falling. Sorry.
Uncle's not in my class.
My legs are falling asleep.
My uncle doesn't have both of his legs. He's actually
I could have been
insanely
rocked.
great.
Should have died. Could have banged my head against the concrete when hit
You
the chair.
could have been
down.
right.
Yeah.
All right, crew. So when we do this on our calculator, that's going to give us roughly 7, a little less than 7, and dividing a little less than 7 by 2.5 is going to give us more than 2, less than 3. We're going to be like in the 2.6-ish category here.
Close.
What is it?
2.47 and then like a bunch.
Okay, so the number we get here is 2.47. Give me the rest. I want, give me like 8.
3, 3, 8, 4.
Okay, we'll stop there. Okay, now the question is, where do we round this? Does that make sense? And the way we decide where to round it is, we say, how many of these numbers are significant? All of them. So 1, 2, 3, 4. Okay. How many of these are significant? All of them. So 3. How many of these are significant? 2. Okay, all of them, 2. Beautiful. So now, the answer has to have how many sig figs? 2. And the way to do that is start from the right. So that's going to be significant. That's going to be significant. And then all of these have to go. But you do have to round. Does that make sense? Don't just cut these off. You do have to round. So what does this round to? It's either going to be 2.4 or it's going to be 2.5. And the question is just, is this over halfway? So is this over halfway? Yeah. 47 is closer to 50 than it is to 40, right? So this would be 2.5. Good. All right. And that is 2 sig figs. Just like the question, just like what we started with. So again, your answer has to be as weak as the weakest number you put into it. Now, if you were going to go do more math with this, we would actually use the big number. We'd use this whole number to go do further math. Does that make sense? We don't actually do our sig fig round until the very end when we're giving our answer. Does that make sense? Because if you round too early, you can mess things up. All right? You can introduce what's called a rounding error where, long story short, just you round at the end. So if we had to go do more math with this, we'd use this number. But if we're giving it as a final answer, we use that number. Does that make sense? We always round our final answers to the same significance as the least significant number we used to develop it. Let's try another one. Okay, do that in your calculator. Oh yeah. That's going to be about 7,500 divided by about 75. So that's going to be about 100, but a little less. That's going to be like 80, 90-ish, which would be 8 or 9, 0.8 or 9 times 3. This is going to be a roundabout between 2 and 4. I think. And everyone can see this decimal place here, and that decimal place there, and that decimal place there,
You know now, look.
that decimal place there.
Decimal place.
I'm sorry. So when we plug all that into our calculator, what do we get? Huh? Huh? Huh?
So
Huh?
our weakest link would
We'll get to that. We'll get to that yet. First, let's just do the math.
2.67043298.
3298 and dot, right? That would,
Is this 4?
sorry?
Is this them?
By the way, I mean, I understand I gave a weak answer saying between 2 and 4, but still, not bad, right? Not bad. Okay, now let's talk sig figs. How many of these digits are significant? Yeah, which is? 4. Okay. This?
5.
Yeah. This one? Yeah. And this one? 2. Okay. Right? Because these are just placeholders. Those 2 are significant, right? So now our answer has to be rounded to 2 sig figs. And every time you do that, you're going to say, okay, this is either 2.6 or the last number could go up. So this is either 2.6 or it's 2.7. Our job is to figure out which one. 2.6 or 7, which one? We look at what comes after and we say, is it above half? In this case, it is. 67 is closer to 70. So this would be 2.7. How's that feel? And that now has 2 sig figs. Now again, if we were going to use this number to go do more math, which one would we use? We'd use the big whole thing, which is why we usually write this down and then round it. Does that make sense? Because if we have to go back and do more math, don't use the rounded number. Use the big thing that your calculator spits out. Does that make sense? Now, mind you, with dimensional analysis, we try to always do things in just one calculation, right? To make our lives easy. But if you do have to do a few calculations, you don't want to round until you're done everything. Does that feel okay? All right. So those are the rules for multiplying and dividing. One note, whole numbers. Like it says here, if we're calculating power and we were saying, well, okay, we have 1.2 kilowatts from this hairdryer I'm using, and we're using 2 of them. What's 1.2 times 2? 2.4. Now, if we count sig figs, we'd say, well, how many sig figs is this? 2. But this isn't 2 that was measured. When we have 2 hairdryers, you don't measure that, right? We don't get out the hairdryer measuring scope and like put the hairdryers on there and it says, oh, there's 2 of them. How do you know there's 2? You looked and you said, there's 1 and there's 2. So that doesn't mean maybe when we count that, is it like, well, maybe I have 1.7 hairdryers. That doesn't even make sense, right? So counted numbers have an infinite number of sig figs, right? If it is counted, not measured, then you don't have to worry about it, which means the answer should actually have 2 sig figs here because that's our least significant number. Does that make sense? If it's a counting number or something else that's exact. For example, if we were multiplying by a fraction with dozens, we're like, oh, there's 12 dozen in 12 and 1 dozen. You wouldn't say, well, 12 has 2 sig figs and 1 has 1 sig fig. We'd just say those are all infinite because we mean exactly 12 and we mean exactly 1. Does that make sense? So anytime you could say in your head, oh, I mean that exactly, precisely, no change, then you don't have to worry about this. You can skip it. You can say it's fine. It's not going to change anything. In other words, if somebody says, take that number and double it, you don't have to be like, okay, they told me to double 125. Doubling 125 is 250, but I have to round that to 200 because I only have 1 sig fig here. You're like, no, doubling means multiply by 2 exactly, right? Okay, one more rule, addition and subtraction. We don't do this too much, but addition and subtraction doesn't use sig figs, all right? Doesn't use sig figs. Don't count them, all right? If you're multiplying and dividing, we use sig figs. If we're adding and subtracting, we just use decimal place. Just use decimal place. So the answer has the lowest or least significant place value. And I'll tell you what I mean by that. If we lined them up and we said 118.2 plus 2.751 plus 30.0 plus 95, add those all together on your calculator, tell me what you get. Actually, can we do one thing because this could be confusing? Can we say 2095 for that last one? Yeah, because otherwise it could look like it was sig figs, and I don't want it to look like it's sig figs. So let's see if I can do this in my head. That's a 1, 5, that's a 9, that's 10, 15, so that's going to be 5. We had a 1 here. That's going to be 2, and 3 is 5, and 9 is 14. Carry the 1. That's going to be a 2 because there's a 1 up there, and a 2 there. 2,245 decimal 991.
God.
951. That's a 5.
Yeah.
All right.
You got it.
Yeah, look at me.
Good.
Woo!
Designed to use that.
Okay, so now here, what you would do is you'd just say, which one of these has the fewest decimal places? Well, this number has one in what we call the thousandth column, right? This one has one in the 5s. All of these have them in the 10s, but this guy here doesn't have any of those. So since this guy here doesn't have any of those all have to go away. Does that make sense? But you do round, which means this would equal what?
2,246.
Good. So you just have to lop off any decimal places that one doesn't have. Does that make sense? And they don't necessarily have to be after the decimal. Even though we call them the decimal places, they could be before. Let me give an example. What if we took me and we said I weigh 120 kilograms and I'm standing on a scale, and while standing on the scale, I pick up my dog who weighs 8 kilograms. Actually, let's make this so let's say I weigh 120, and I don't know if that might be 122, that might be 123. I just say I like that. And I pick up my 8 kilogram dog, and I pick up my 2 kilogram guitar, which weighs 2.25 kilograms. And let's say my dog I've had measured recently, and it weighs 8.8. And then I pick up my backpack that weighs 43.1 kilograms. I weighed that. And then I go step on a scale. What am I going to weigh on the scale? Well, we add these all together. That's a 5. 8 and 2 is 10, and 1 is 11. So there's a 1 there. We carry the 1. 1 and 8 is 9, and 2 and is 11, and 3 is 4. So that's a 4. Carry the 1. 1 and 2 is 3, and 4 is 7, and 1 with nothing else. So can you do that for me, please? Make sure those actually add up. Is that right?
Yep.
Okay. So the problem is this first one, actually, I only measured to the nearest 10. Does that make sense? So everything else down here is insignificant. Does that make sense? So where would I have to round this to? We add it all together. We do the math first. But because I might have been 122, which would bring me to 176, I might have been 198, which would bring this down to 172. So we actually have to round this to 170. Does that make sense? So for adding and subtracting, we just use place value. And sometimes writing your adding like this can actually help. But you don't have to. You could just look and say, oh, my number with the least significance is that 20, right? Which is to the nearest 10. So that's where I'm going to have to round. So adding or subtracting, we don't use sig figs. But in this class, we do very little adding and subtracting. Mostly we do multiplying and dividing. And for multiplying and dividing, we count sig figs. Does that make sense? All right. You got some time left. In the time that remains, we got a lab tomorrow, so you can prep for that. You can work on other things if you need. Lab 3.2 is online. We'll get to it then. Yes, speaking.
You sent up stuff for your period 2 class.
Yeah.
The times.
Is Heimpel there? Is she not seeing it? Tell her just.
There's something up there with the 10. Yeah.
Yeah, it should be an onion skin lab. If it's not there, just tell her to come home, and I will go get. She's been up there for like 10 minutes now. Tell her I'm sorry.
No, we came back. I think she came back down.
Oh my god. Okay, we don't need to like make 16 journeys. If I've screwed something up, you just tell me and I'll deal with it. Yes, sir. Oh yeah, let's grab it. What makes you sad?
I'm still coming out on his birthday.
Yeah, please. Wouldn't you like to know? It's our none of your business lab. It's one we did right now.